So I'm going to go ahead and pop the chat out for us. And if you guys have any questions, feel free to put them there. I'll be checking on the forum posts every once in a while. But let's go ahead and get started. So today's lecture is going to be on style transfer. And well, it's going to be a mix. It's going to be style transfer. We're going to look at deployment. And then we're also going to look at EfficientNet and how you sort of can take any pre-trained model or not pre-trained and load it into the framework and kind of work with it. So I wanted to get this done yesterday, but just life got in the way, and I apologize for that. I'm in college, so I'm trying my best here. Now we're going to be working out of 05 Style Transfer, 05 Inference, and 05 EfficientNet today. Now if you decided to pull the notebook a little bit before the class started, go ahead and run it again. I just put some fixes up on there. Now the first thing is a few more minor announcements. So Jeremy came out with a paper, and for any of you doing research, that's invaluable because that is a direct source to the library for us. So highly recommend that you guys go read that. It is on my reading list to do this weekend. It's going to be talking about the new version of the library, and all the code examples are under the assumption that the new library is going to be released. Now what that means is anything with fastai2 is going to become fastai. Jeremy actually just talked about this. So go in with knowing that. Otherwise, highly recommend the read, as I'm going to be doing it shortly after this. Besides that, I believe that was one of the most important announcements. I'm working on getting the heat maps working and whatnot. It's a little bit tricky, so in the end it might be a group sort of collaboration if you guys would be interested in that. Otherwise, that's what it was. Colab came out with their Pro version, and if any of you work out of Colab like I do, I highly recommend that you get it. I bought it like the day that it came out. It's $10 a month and very easily worth it. If you don't have it, you're not guaranteed a GPU every single time. And most of the times when you do get a GPU, if you have Colab Pro, then it's going to usually be a P100 or a T4, something decent instead of the K80 that most people will get. So when you're running through my notebooks and you notice that the times might change a little bit, that's because I'm running Pro and I'm running a P100. So besides that, let's get started. So for style transfer to really work, you need a P100 GPU to make it work well. So the first thing that you'll see here is we're going to check for the GPU. Now I'm running a P100, but if not, this might change in the future. You can attempt to force Colab to give you a better GPU by doing by making a 1000 by 1000 by 1000 tensor. Now, please don't abuse this because, you know, we don't know if Colab's going to fix that, which they probably will. And if a lot of us do it too much, then you know they're going to fix it very quickly. So please try and use this only when you absolutely have to. But otherwise, let's get started. So style transfer. A lot of the stuff that we're going to be working off of was made possible by Lucas Vasquez on the forum. Him and I worked a lot on trying to get style transfer working, and he pushed most of it. So what are we going to cover today? So we're going to cover custom loss functions, custom models, utilizing the new notebook dev library that Jeremy and Sylvain came out with, and how you can kind of work with deployment code a bit more. I know we went over it initially back in week 1, week 2, but I wanted to revisit it because you know, we're all learning, and there's a few different ways that we can go about things a bit better. So first, let's look into a light introduction to what notebook dev actually is. So if we go to github.com/notebookdev, fastai/notebookdev, you can see that we have this wonderful little repository here where you can create delightful Python projects using your Jupyter notebook. And for those of you getting started on a project, you can fork the template over and just work out of Notebook Dev. There's already actually a template available. If we go over to the Notebook Dev template right here, and you can select use this template, it'll make a copy for you of wherever you need to be, and everything will be set up for you. Now we're going to use it, even though we're not per se making a library right now. We are going to be using some functions in our notebooks that we're going to want to use later, either for later training or for deployment. So it's still useful for us, even though it's not a library. So what it will do is it'll create documentation along with our .py functions. Quick question, what is the GitHub site for this notebook? So this notebook is 05 style transfer, and so that's going to be under the Mueller ZR Practical Deep Learning Coders, Computer Vision, and then we're doing 05 Efficient, Inference, and Server or Style Transfer. So we're starting with the Style Transfer notebook and working our way back up. Now the cool thing with Notebook Dev is you build an entire library off of just notebooks. So what that means is we create our documentation along with the actual imported Python files that we want. And let's go over a few of the sort of terminologies. So we have default export, hide, and export. Now what each of those mean are a bit different. So default export says what we want to call the generated py file. So you can see here in the very first line of the notebook we have default export style transfer. So we're going to expect it to be style transfer.py. And then hide is specifically for the documentation. So if there's, say, a test that we have or some sort of import that's not necessarily needed, then we can go ahead and hide that so that way our users don't see it. And then finally, export. Export is used for any sort of code that we want pushed to our .py. So on a whole, that's going to be any libraries that we take in along with any of our functions. And what's also required is a Notebook Dev show doc every single time. Now you're going to want to hide this because the documentation doesn't really need it. We assume it already. But just know that's always needed. Otherwise, let's start looking at the cool stuff. So we're going to use the Vision, Basics, and Callback library as usual for any sort of vision task for our style transfer. Now, what is style transfer though? So style transfer utilizes something called feature loss, or also known as perception loss. And essentially what we do is we take a look at the input features that our model has versus our output features. We compare them and see what's kind of the same, what's not, and adjust accordingly. We'll see more whenever we start building the loss function. And it's an image to image, so we send an input in, we send an output, and they're both image types. And usually you'll have a loss function that is a network in itself. This is where our perceptual loss function comes in, where it measures the difference in the styles. So for us, we're going to be using a VGG network. So we're going to be using VGG 19. It's a small CNN, very small, pre-trained on ImageNet that only has 19 layers. So I've set it up to where you can use either VGG 19 or 16. But let's take a look at what we do. So the first thing we want to do is, since we're not training this is strictly just evaluation, we want to get a pre-trained model, gather its features, turn it to CUDA, because we're going to be running everything on the GPU, and set it to evaluation mode. Now what that means is we don't keep track of the gradients and our weights never change. And then so we're going to want to be able to get the internal activation features from our model. And in order to do that, we first have to get rid of the head and internal activations, basically. So we're going to make sure that in our EfficientNet, everything that requires any sort of gradients is set to false. And now we want to go through and extract every single one of the activation functions. Now the reason for that is the activation function doesn't really learn anything, but it has all the information from the previous few layers. And so we can use that to extract our features. This could then be applied to any other model where you can figure out where those activation functions are, extract them from there. So here we're going to have two different configurations. This is just like our layers before, where we can separate a 16 and a VGG 19. And now we're going to try and surmise all of that into a quick sort of function for us. Part of this is going to be for deployment code, but part of this is let's get rid of any extra code in case we want to work on style transfer and we don't want to write multiple things over and over again. Jeremy's rule of thumb is if I've written it twice, then store it somewhere. So we'll go ahead and grab a EfficientNet that's either a VGG 19 or 16. Go ahead and search the configurations, extract the features, and return our EfficientNet along with the features. Now, since it does have an underscore, this is a private feature, so our users can't directly access them. So we're going to need a getFeach function that takes in a string for an architecture, make sure if it's pre-trained, and goes ahead and grabs the hooks from our layers from our model, because that's really what we want. We want the hooked activations, and we're going to be training this sort of feature comparison model based on these hooks. And a few of you had questions of why am I running part of the lectures in Jupyter Notebook versus nbdev or versus or Colab versus, say, Notebook Viewer. That just kind of depends on how long it takes for the lecture to really go and how long for the model to train. We're not going to be training in Colab, but there's specific functionalities that I need you guys to learn. And so that's why we're going to be doing a lot of the lecture in Colab today. Make sure we don't have any other questions. Awesome. All right, so now let's go into the loss function. For the loss function, we're going to need an image with some sort of style that we're going to be wanting to replicate. The original image that we're actually passing in, along with the activations from our encoder, that feature network that we had. Now today we're going to be using this particular styled image. Lucas and I kind of just went with this one. It worked pretty well for what it was worth, and so we're just sticking with that one for right now. You're more than welcome to play around with any other image that you want. Usually anything that's a bit more abstract has some bit more clarity to it. Can I explain hooks a little bit more? I can try to. I'm still unfamiliar with a lot of things, but basically hooks gathers the weights at particular layers. And so we can basically take snippets from our model at where they are and work with them. So we can get their activations, get their features, and play around with them. I hope that kind of clears things up a little bit more. From there, though, we can go ahead and grab the image. So this will grab the image for us, and we're going to go kind of look at the pipeline and how we can work with the data data loaders for just one particular item, because we want the raw tensor value of this image and we don't want it transformed in the sense of size reduction, activations, not weights, right? Well, the activations themselves are the weights. So any sort of well, I'll be honest, I'm a little bit unfamiliar with the difference between the weights activations and all of that stuff. We can further discuss this later after the lecture in the study group, and we can go from there. But for now, let's kind of just focus on the technique. So we're going to want to create a pipeline that converts our input image into a tensor with the only sort of transformations being applied to it being the toTensor and normalizing. So we're going to use datasets and data loaders for this. We're going to pass in our file name and say we just want to do PIL image create and then make some data loaders where our after item is just toTensor, and after batch we convert it over and normalize it. And if we take a look here, we can see that our show batch shows that we just have our regular input image with our transforms applied. Now in order to get this raw value, the best way that I've found is to just do a one batch and grab the X because it is only one item. I'm sure there is a better way, just this is what I was able to find within the last few days. So if we take a look, we can see that we have the full-sized image, and now we can make a quick function that goes and grabs a stylized image from any URL that we want. And now we want to grab those features from the image that we want to train with. So we're going to call our feats function that we made earlier and pass in that tensor image. And if we look at their sizes, they correlate to where those hooks were, where we grabbed the layers of our model. And now we can bring them down to where it's sort of a channel size instead, and we can focus more on the actual values themselves inside each channel. So we can see that we went from 512. We basically got rid of the other excess and kept it as 256 by 256, 512 by 512. And then finally, to return the features, we want to grab everything but that first layer, or that first one, I should say. And we're almost through all this confusing nonsense. Now, let's take a look at why that was kind of important when we go to the loss function. So we're going to have 3 different items in our loss function. We're going to have the features that we extracted from our encoder, or something called a style loss, and something called an activation loss. So the style loss, basically we have input features and output features, and we're just going to calculate mean squared error for all of the stylized features. Basically compare how they look compared to our original image. And then we're going to get into what's called feature loss. So the important bits that I want you guys to take away from here, even if you don't understand quite the concept, the higher level concepts per se, because I'm still struggling with them. The important bit is how we can make these custom loss functions, and how does fastai expect them. And so here is where we're going to make our loss function. So the first thing is each time that we pass an image in, we don't want to update the encoder's weights because we don't care about them. What's training is our actual model, not the loss function model. So we're not going to keep track of any of the metrics. That's what this is doing right here. Now our forward is exactly like our model's forward. So every time we call it, even in a loss function, it's going to go through it. So we're going to get our predictions by running them through the feature extractor, calculate the style and activation loss, store those away, and then just return a sum. Most of these complex loss functions just take 2 to 3 different calculations and then return a sum, unless it's weighted. It's nothing necessarily too crazy. And then every single time that we want to do reset metrics, this isn't something in the fastai library, it's just something we do. And all we're doing is just resetting the style and content losses. And we're going to keep track of that every time we call an an add loss. Now our activation loss just does a mean squared error of the activation layers themselves, and that's about it. So now we can call our loss function to make an instance of it, because remember, since it is a forward, we're actually, anytime we're going to be doing anything, passing in an x and a y to the function instance itself. And now we can build our architecture. Now, as far as what each of the layers are doing, we'll try and walk through it a bit. And you'll notice that, especially when we get to the model declaration, it's not exactly the cleanest, but when I went to try cleaning it, it's about as clean as we could get. So there's certainly ways you can improve it, but this is just an example. So we're going to create a variety of layers for us to use, similar to how we made the res blocks. So the first thing we're going to want is a reflection layer. And all a reflection layer does is, first we take in our input, and we're going to do some reflection padding on it, and then just call a convolutional or a conv2d layer. That's it. So reflection pad, conv2d. Now, to build with that, though, we're going to make a residual block. Now, a residual block has two of those layers with some instance normalization and an activation. And then towards the tail end, we're going to sum out the original, which was our x, and whatever our output was after we traveled through all of our instance norms layers and whatnot. And then we're going to have an upsample convolutional layer, which basically this is another reflection layer, but we also have some upsampling done in the very beginning. Now, each of those are based on their own separate papers, and I'll link those in the study group after the lecture is done, if you want to read more about where the technique sort of came from that people figured out what works. And now let's go through and declare another model. Now this is where I mean it's not exactly the cleanest, but we can understand what each of them are doing. And so we're going to have a series of reflection layers that start at 3 and then go up to 128, have our residual blocks, upsample a bit more, and then finally deconvolutionalize with one last reflection layer that returns again 3. And if we look at our forward, it's not exactly the cleanest, but it's very explicit in showing what it does. Now, if you're unfamiliar with how to read this sort of notation, we're calling the first convolutional layer with our input, and then send it to an instance norm, and then to a ReLU activation. So that's what this is really meaning. It's expanding outwards in the function calls. And so now we make an instance of our transformer net. So let's take a look at how we build the data block for this in the data loaders. So we're going to use the Cocoa sample data set. It's just a whole bunch of images that aren't too big, and they can help us with this project. So our data block is going to pass in an image block and pass out an image block. And our only transforms are going to be resizing and normalizing. Now, if you notice, we don't pass any sort of get y into our data block. This is because our x's are our y's. And if you don't, then fastai2 will assume that your input is your output. And so here we don't need any sort of get y. Then finally, we can pass in a batch size of 22. Now, we're going to start at a small size and then blow it back up. When you do so, you are definitely going to have to decrease that batch size, usually to like 4, I think, if you decide to go 224. And so if we look, our only augmentations were resized, so they look very similar to how they were before. And now we can make a custom learner where we pass in our data loaders, our architecture, and finally our loss function. And a nice way to check to make sure if you're playing around with models, this is something I found when trying to refactor. The nice thing about Learn Summary is it'll tell you how many total parameters a model has. This is especially important when you're trying to figure out why two models aren't necessarily acting in the same way, because sometimes those parameters might be different, and that's very important. So now we can just, find our learning rate and go ahead and fit. Now here, since every single time we pass a batch in, it's being updated, the styles being stored away, and the models being affected, we don't need to train for more than one epoch at a particular size. And so we can just fit for one. And now we can take a look at how some of those results looked. And you can see that we started off with a little girl, and now we have something similar to our style image. And if you noticed, whenever we started declaring various cells that we wanted to keep track of, we kept this export tag on it. We'll see why that's going to come into play a little bit later when we try convert this into something that we can use whenever. So let's try and predict on an image. All right, so I have a cat image that I have saved away on my computer, and we're going to try and predict on it. And what we find is it doesn't exactly have the best quality. Why is that? Because when you do predict, it'll run the same training transforms. And here, it's actually okay not to do that, because we are really only running one image at a time for the most part. And so let's look at how we can get away with doing that and just sending in the raw image to the model and storing that image away now. So first thing we're going to do is create a data set similar to how we did for the stylized image, where we're going to pass in our file name, just create an image, make it a tensor, and normalize it how we expect. And then what we can do is actually grab one batch. And the first instance in the batch will be our image. And so finally, we can just run it through the model. And we want torch no grad because we don't want to store any of the gradients on the image. We're not trying to train the model. We just want it on evaluation mode. And so now if we go through and look at it, that looks much more like sort of what we would expect out of our stylized image. Now for homework, I want you guys to increase the size to 512, similar to how we did in the segmentation. And you should notice that the results are a lot better. Now from here, if we want to export our model, there's a few things we have to take care of, and specifically the loss function, because if I just try and do learn.export right now, well, now it works, but that's because I went over it. What it will give you is, if I do, let's try this, learn.lossfunc equals lossfunc. All right, now it's in our style loss function. If I do learn.export, you'll notice that we get this strange can't pickle local object get feats. And so what that means is we declared get feats in our notebook, and it doesn't know how to serialize that away. Now, there's a few ways that you can go about doing that. The first one is to non-serialize it, which is kind of hard to do. The other option is just make it into a function that we know can. Any of the standard fastai functions will get serialized well, so we're just going to use cross-entropy loss. Now, we already saved away all the functions needed to recreate our loss function if we ever needed to. But when we're going into serving our model, we don't care about that. So we can go ahead and declare it as cross-entropy flat, and then just do a learn.export. Now, when you do export, the model itself will be saved over into this models folder. and specifically stage1.pth. And if you do export, it will actually just go, sorry, when we save, it'll go to models. When you export, it'll go to whatever directory you declare. So here, my model's right here. And finally, let's go into the notebook dev stuff and why the export comments and everything was very important. This is a quick way for you to make a configuration file that notebook dev needs. Even if we're not per se writing a library, it allows you to do notebook to script, which is the important bit for us. Your username can be anything, your library can be anything, but the important bit is that we create a configuration file. And then we're going to reset it so that way it gets used to this new setup that we have. And finally, we can do notebook to script. And when we run this, it'll give us a message saying that we converted O5 style transfer. Now, to get to that point, you're going to want to go to File, Download IPython Notebook, and then re-upload it to the base directory. So you can see I did so. It's right here on O5 style transfer. And now if we want to get to this style transfer.py file, we're going to go into mylib, and there it is. So this is sort of how you can do style transfer in the fastai2 library, or really any sort of style loss or feature loss technique. It's not very different from how the previous versions were, minus some updates to the loss functions. But let's go look at how we can do that from a server now that we have everything saved away. So I've got this one stored away as deployment now that it's going to export as. But first thing we're going to want to do is upload the style transfer Python file. And we're going to use the vision and the style transfer file that we just made. Now, when it comes to deployment, the style transfer file is mostly going to help us with the model declaration itself, because that's needed whenever you call load learner. Otherwise, everything else we're going to pretty much declare in here. So we can call load learner, and in our case, we're not going to be running in a GPU environment, and so we're going to say CPU is false. From here, we're going to use any sort of file name we want and create it just in the same way. Make our data loader and grab a batch, and then grab its raw output. So let's wrap all of those into functions that we can use. So we're going to use getLearner, load a learner, and then make our data sets how we want. And then finally, we'll want to save it away. Now, the important bit here is, and I'm not sure exactly if it got exported how I wanted it to. It did. So since we're sending in raw input, we want to do it with a batch size of 1 every time. So later we'll look at how we can adjust this code to take that into account. But finally, let's look at how we can save images away, because we don't have to always convert everything to a PIL image. Torch Vision actually has a save image function where we can pass in any sort of tensor, and it'll automatically save it to whatever image to an image that we can work with as regular humans and not a computer. So let's try and put all of this together. So we're going to want a path that we save our results into, get our learner, and then check to see if we have more than one file name. If we do, then we're going to make multiple data loaders and store those away. Otherwise, just make one, and then store and save our outputs. So I have a quick example here where I took our cat JPEG that I made earlier, ran our inference, and if we look at our results folder, we have a whole bunch of stylized images. And if we want to store all of these functions away to use on our deployment, then you can go ahead and use notebook dev again for this, and you'll be all set. But that's sort of how you can use style transfer and then also do a bit more different approach to deployment with the V2 library. So I know it wasn't exactly one of the most technical explanations that I could give. I highly recommend the style transfer lesson that Jeremy gives. I'm also going to have a link to that because it goes over the feature loss technique very, very well. And I will note this is different from a GAN. So it doesn't quite use everything that a GAN has. And for this sort of technique and what we're working with, it actually can work a lot better than a GAN would. A prime example of that would be Jason Antics deoldify. In the beginning, he did use a GAN for a while, but eventually he found more success when converting it over to this sort of style transfer technique. So from there, are there any questions? And I can do my best to answer them. Otherwise, we can answer them on the forum together. All right. If not, then let's go ahead and get into something a bit more fun and can be applied anywhere. And that is EfficientNet and Custom Pretrained models. And so what we're going to cover here is how to use any sort of PyTorch model, their pre-trained weights, and set it up kind of to how CNN Learner builds their models. So we're going to go back and revisit pets, and this just grabs all of our data. And the reason for that is we're going to focus more on the models. So we're going to use Ross Reitman's repository, which is a whole bunch of PyTorch ImageNet models. And I mean, it is very impressive with the work that he has done. Anything that comes out with TensorFlow, he usually tries to recreate it in PyTorch and makes it easily accessible for us. And so that's why I want to utilize it for our models. All of his models were trained on a 224 by 224 image, and so let's try and work with that. So it's a nice, very easy pip install, and from it we can use this create model function to grab and pull any of the weights. So we're going to go through two different ways. The first one is just a very direct way of loading the weights in, which is through this sort of create model function. And then we're going to try and recreate that ourselves. That way, if you don't have access to something like that, how do we load that in? So we're going to use the EfficientNet B3A architecture. And if you're using Tim's library, then it's just as simple as create model, pass a string for the name of it, and then pre-trained equals true. Now, if we create a CNN learner, you'll notice that we have a custom head that has this adaptive concat pull to Ds, batch norms, linears, and all of this other fancy stuff. Whereas if we look on EfficientNet, we don't have a head to our model. It doesn't exist yet. And so most of the time when you try this, you'll get this EfficientNet object or ResNet object does not support indexing. So let's take a look at why. When we made our head, we actually created two different groups. One that was the entire encoder and one that was the head, whereas EfficientNet doesn't have such a thing. It's not wrapped in a giant sequential object because that's all that's really happening there. So let's look at how we can do that for our particular model. So if we look at the EfficientNet model and go all the way to the very end, we can see that we have some global pooling and linear layers as the last two. So let's say we can create a body. We saw that we can do a call to create body with some architectures, and so let's see if it works here. It doesn't though. Why doesn't it? Well, if we take a look at how create body is expected, it expects our architecture to be some sort of callable function. That's what the resnets are. And then it cuts. So let's try and make this generator for our TIM models instead. So we're going to go ahead and call create model, which was that create model function we declared earlier. And now it's how this is expected. And that's all there is to it. And so if we try it out with an EfficientNet v3a, we can see that we have seven different layer groups. And if we take a look, we can see that we have 0, 1, 2, 3. And if we slowly follow along through here, we can find 4, 5, 6, 4, 5, and 6, sorry. And if we look, we've popped off the last few layers. So now we can go ahead and take the number of features that our model had at that tail end right there and create a head out of it. Now, we want 2 of these though. And the reason for that is our heads use 2 pooling methods, average pool and max pool, and so we need enough to pass it through there. And so this will create that for us, and then our output we want to be the number of classes that our data loader is expecting. And so finally we just wrap it together into a neural net sequential. Initialize the new head, and now we have those 2 models, or those 2 layers that CNN Learner makes. Now finally we can make a learner and pass in our data loaders, the model, and the loss function we want to use. Let's take a look at the model. So if we go down, it didn't pick up that we don't have some non-trainable parameters. Why is that? Well, CNN Learner will also call freeze, which will freeze up to that last split. So if we call freeze after making our model now, we also have to pass in a splitter. Now, default split is just assuming that the last or the first layer group is our encoder, the last one is whatever we're expecting, and so that's why we did that 0 and 1 split. And so here, if we go down and look at our non-trainable parameters now, the head of our model is trainable, and our encoder, or that resnet, is no longer trainable. And so finally we can fit and just train our model how we normally would, unfreeze, train the rest of it, and save it away. Now, the things with EfficientNet that you got to watch out for is that was relatively easy to train, but they can be very finicky to learning rates. And so it's kind of a touch and go seeing what breaks and what doesn't. That's especially what I noticed here. I tried to stay towards a slower learning rate because anything too fast in the model would tend to break. But also, so you can see that we have like a 5.2% error rate that didn't really outperform the ResNet per se, but that's okay because this particular model is 57% the size of a ResNet. So we almost cut its number of parameters in half and was able to pretty much maintain its accuracy. And so now let's go into something a bit more different, which is what do we do when we don't have, that fancy library that Ross made, and we just have some pre-trained weights? How do we transfer those over? For example, this could be something like experimenting with a different model, or something that's come up on the forum a lot, which is transfer learning twice. And so what that would be is something similar to I trained a model that can identify 20 different kinds of birds. From there, I want to create a binary model that says whether or not the bird is a blue jay or not. Well, I want to use the weights from my bird classifier because that fits that particular task a bit better. So to do so, we're going to take our cats and dogs model and try and train ImageWolf on it. So this just goes ahead and gets ImageWolf for us already. And now we're going to create our body, create our head of our model, go ahead and make it, and apply it. And this is exactly the same as before. Now, we want to load the weights from our previous model into the new model. And if you try and do a learn.load here, you'll get a size mismatch error and everything will break basically. It won't transfer anything over. So let's look at how we go about fixing that. So all of the weights to all of our layers are stored away in the state dictionary. And we're going to use a technique that Virat made on the forums. And this is the link to it with the general function, and I've used it so much that you can see it's actually bookmarked. And so let's look at what we're actually doing here. So this is the function that he came up with. And essentially what we do is we pass in our learner the name of the pre-trained model's weights and what device we want to use. And we're going to grab the state dictionary from the new model. Now with fastai models, generally we also store away the optimizer state. And so you might need to index specifically into model. If you notice that this tends to not work, and it'll say like model attribute not there or something, then get rid of this model part. But we also want our learner state dictionary. And so we'll call that learn state dict. From there, we're going to check in all of the current dictionary if anything in our learner's dictionary is also in our new dictionary. We're going to copy over the weights. If not, then we're going to skip it. And if it's not even there at all, then we'll just say it wasn't there. Finally, at the very end, we're going to want to load this transferred state dictionary into our learner's model and return it. And so if we call transfer learn and we pass in our learner and the stage 1 that we made earlier with the dogs and cats, we can see we get a shape mismatch at 1.8.weights. Well, what exactly does that mean? Well, that's an index. So if we index into what 1.8 is, oh, okay, that's that last linear layer where we have our in features as 512 and our out features as 10, what we changed from last time. And so everything else is exactly the same. Now we can just freeze our model and train it again. And now this is our transferred model, okay? So we got up to about 89%. And just for comparison, to make sure it truly was transferring, I've also provided an example of what happens when you don't run pre-trained. And you can see the best we got was 15%. And so this is how you can transfer over basically any sort of model where you keep the architecture the same and maybe change its task to something a bit more specific or something. But now you aren't limited to just A, ImageNet, and B, you can use your own pre-trained weights instead of trying to borrow off of other people's. So next week, we're going to go over bounding boxes, object detection, and bit into key points. This week, you could tell I was very much out of my comfort zone, but I wanted to give you guys this because it's something that's been asked on the forums with specifically style transfer and how to keep everything updated. So a lot of these lessons, I will be out of my norm because I'm not that far into the course to where I understand it very well. But I at the very least want to show you guys these techniques. That way, those of you that are wanting to become experts in those particular areas or do need to use it, you understand how to apply it into the framework. So next week we'll do bounding boxes and key points, And then from there, I'm still up in the air as to what the next lesson is going to be. I've got to see what sort of comes out of this week. But otherwise, thank you guys for watching. I greatly appreciate it, and I will see you all next week, where we're going to be hopefully live on that day.